Hi everybody, I'm Greg Fishel and welcome to bonus weather video number 2 for this week. And I'm just going to warn you up front, maybe uptight as well. If you don't like math and you've never even considered looking at anything relating to calculus, it's time to go grab a Miller Lite, okay? This is going to drive you crazy, and I'm only doing this for people that are like math and maybe have had some background in it and want to know how it relates to meteorology. So you won't hurt my feelings if you don't watch this. Of course, I guess I have no way of knowing if you watch it or not. But anyway, I just wanted to warn you up front that this is heavily mathematical. Okay, so let's go on ahead. We're going to talk about something called thickness, and we're looking at the thickness between two surfaces of constant pressure. And you can sort of envision this, that you go up different heights around the world at different locations to get to a certain pressure. So a constant pressure surface is, up and down and up and down and up and down, but everywhere along that surface it's the same pressure, okay? All right, so let's move on ahead here. Luckily for us, there is a thing called balance of forces. We have the force of gravity directed downward, and since the pressure decreases as we go up in the atmosphere because there's less air, then the pressure gradient force is directed from high pressure to low pressure. Those two forces balance each other, and thankfully they do, because otherwise the atmosphere would either collapse or escape into space, and that wouldn't be good on either front, no pun intended. So there's an equation called the hydrostatic equation, and that little symbol to the left of the P there, just basically think of that as delta, or change, okay? So the change in pressure divided by the change in height, or with respect to the change in height, is equal to minus times the density, that's the Greek letter rho there, times the gravitational constant, which is how quickly objects accelerate as they get pulled toward the Earth by gravity. Okay, so that equation basically describes that balance of forces that I just talked about. Now, there's another equation called the equation of state, and it states that the pressure is equal to the product of density, that Greek letter rho, times the gas constant times the temperature. So if you solve for rho, you get rho is equal to P over RT. And you can substitute that back into the equation in the upper left there. And so now you have this, dP dz, same thing on the left side of the equation, but now it's equal to minus Pg over RT, okay? Pressure times the gravitational constant divided by the gas constant times the temperature. Okay, you with me so far? All right, so now we have that equation, and what we're going to do is something called integration, where we're going to integrate that equation from the low pressure surface to the higher pressure surface, and from the lower height to the higher height, okay? So we're going to call those P1 and P2 and Z2 and Z1. When you do that, oh, I'm sorry, and there's one other little trick here. To get rid of that minus sign in front of the G, all you have to do is swap the P1s and the P2s. So now the P1 is at top, the P2 is bottom. So we're going to use this. We're going to assign P1 to be 1,000 millibars, which is close to the ground, and P2 is being 850 millibars, which is about 5,000 feet up. And then that's equal to G over RT, and we're going to integrate Z from Z1 to Z2. That's still the same, from the lower height to the higher height. Okay, so when we do that, and this is, I'm not going to go into all the mathematics to prove this, but what it says is that the natural log of P1 over P2, okay, so that would be the natural log of 1,000 over 850, is equal to G over RT times Z2 minus Z1. And we're going to call Z2 minus Z1 the thickness, okay? So let's solve for the thickness. And we already have all the information we need here. We can figure out what the natural log of P1 over P2 is using your favorite calculator. We can let P1 be 1,000 millibars, P2 850. We're going to let the temperature be 273.15 Kelvin, and that's the scientific unit. It's equal to 32 degrees Fahrenheit. Why are we doing that? Because we want to find out what is the thickness when the average layer, or average temperature of that layer, is freezing. Okay, because it may give us an idea where the boundary between rain and snow is going to be. R is equal to 287. which is the gas constant, and the gravitational constant, again, is 9.8 meters per second squared. And the answer is 1,300 meters. And we call that the critical thickness. During the winter season, when we're trying to assess where that boundary between rain and snow is going to be, we take a look at where that 1,300 meter thickness is forecast to be. Now, there are exceptions. We're talking about an average temperature over a 5,000 foot layer. So what if it's really cold at the top of that layer and fairly warm toward the bottom? Let's say it's 25 at the top of the layer and 40 at the bottom. You may get a few flakes mixed in there, but they're certainly not going to stick, okay? By the same token, it could be 25 at the ground and 40 up there. And so then you have an ice storm, either sleet or freezing rain, depending on how deep that below freezing layer is. Or if it's just a normal lapse rate in temperature, then it would probably correlate between rain, or the boundary between rain and snow. So there are some exceptions, but it gives us a good first guess as to where the boundary between frozen and unfrozen is going to be. Okay, that's it. Hope those of you that are mathematically oriented enjoyed that, and I hope those of you that were not or are not mathematically oriented did something more fun in the meantime. All right, that is bonus weather video number 2 for this week. Hope you have a wonderful, wonderful weekend. We'll keep you updated on Fiona. I'll probably send you some messages over the weekend just to give you an idea what's going on with that. And we'll see you back here again on Monday with the next daily weather update. We'll see you then.